Alright, so here we're going to follow on from the last video that described the E2 reaction and see if we can understand how to tell between when we see the two mechanisms of E2 or Sn2. And there's several things we want to use to be able to figure that out. The most important is the identity of the substrate. In other words, whether it's primary, secondary, or tertiary. So primary, secondary, or tertiary. If you watched the last video, you'll know that primary substrates, from what we've seen before, favor the Sn2 reaction. You would have seen this in a previous video as well. And then tertiary substrates favor E2 reactions. Now, when we're talking about E2 and Sn2, we're talking about strong bases and strong nucleophiles. So we don't need to worry about weak nucleophiles and bases right now. That's for E1 and Sn1. So all of the guys here are going to be considered either strong nucleophiles or strong bases or both. And remember that we'd said typically what is a strong nucleophile and strong base is something like OCH3 minus, OH minus, NH2 minus, something that's small and negatively charged. So this guy is classified as a strong base and a strong nucleophile. In fact, it's exactly the same thing down here. So you can see that if this is a strong base and a strong nucleophile, you can't really tell from this whether it's going to be elimination or substitution. The substrate, that's why the substrate is so important. It's the thing to consider first. So a primary substrate, you've seen before, primary substrates favor Sn2. This guy is a strong nucleophile, it's also a strong base, but we know that primary substrates favor Sn2. Therefore, if the substrate favors Sn2, and the strong base and strong nucleophile favor E2 or Sn2, then we go with the one that favors the most. So this favors Sn2, this can favor Sn2, therefore we see Sn2. And so the product that we get here is simply just the removal of the iodine and replacement with the OCH3. Alright? Simply, that's all the Sn2 reaction is. Alright, that's all this is. So that goes in there, kicks out this, gives us our product, and if you wanted to show the I minus, you would be welcome to do so. Alright? There should be two pairs of dots, not lines. That's my bollocking software. Okay, now let's look at this one. So what sort of substrate do we have here? Well, we clearly have a tertiary substrate here. We have something that's a strong base and a strong nucleophile, so this could favor either Sn2 or E2. So we've got to look at this one and see, well, what does this favor? Let's go back up here. We know that Sn2 is favored by primary substrates. This is definitely not a primary substrate. This is a tertiary substrate. It's going to potentially form the most stable alkene we can. So we're going to get an E2 reaction. Alright, the substrate favors E2. The base, this is a strong nucleophile and a strong base that can favor Sn2 or E2, but this can favor E2, this favors E2, therefore E2 is what happens. Now for the elimination we have to be a little bit careful and label all of our beta products, because what you're going to be asked on a quiz is, if it's an elimination, I only want you to write out the most stable or the major product. Alright, so we've got beta 1, these two beta 1 carbons are exactly the same, and this is beta 2. So we know that we're going to be seeing an elimination. So we know we're going to draw out the 6-membered ring. We know there's going to be a carbon here, that bromine's going to have left. So the question then becomes, well, if this is an elimination, are we going to lose the hydrogen from the beta 1 carbon or the beta 2? Well, we always lose, if you remember, according to the set, we always lose the hydrogen from the carbon that gives from beta carbon that gives the most stable alkene product. And by most stable I mean most substituted. So ideally, you want to form a tertiary alkene if you can, possibly secondary over primary. You can get primary alkenes formed, just because they're not as stable, they won't form as readily. So one of these types of beta hydrogens will give us a tri-substituted alkene and the other will give us di-substituted. And the fact is, one of the hydrogens from one of the beta 1 carbons will give us the tri-substituted product that we're looking for. If this can act as a base in a nucleophile, it's an elimination. This is going to act as a base, so that's going to grab the hydrogen. This carbon-hydrogen bond is going to break, funnel the electrons down into the bond between the alpha and beta carbons, and kick out the leaving group. So if that's our alpha carbon, and that was our beta 1 carbon, where is our double bond going to be? Well, of course, our arrow shows it's going to be right here. Now, I don't care whether you draw the double bond on the outside or on the inside. Provided you draw it between the alpha and beta carbons, that is all I'm looking for. All right. If we were to have drawn the double bond between beta 2 and alpha, we would have got a di-substituted alkene, but this is tri-substituted, so this would be the major product, and so the product that you would show. If you wanted to show the other two products, again, same as we did up above, you can. It's not necessary, but you are welcome to. There's one. And the OCH3- grabbed a hydrogen, giving us also, if you wanted to show that, methanol as a product as well. But once again, the most important products are the carbon-containing products. Those are the ones to show. Now, as with when we talked about the Sn2 reaction, potentially the problems potentially come when you have not primary or tertiary, but a secondary substrate. So let's look at a couple of others here. All right. I have two examples of secondary substrates. In fact, I have exactly the same thing. This is secondary, and this one is also secondary. So, as you would imagine, because primary favors Sn2, tertiary favors E2, well, secondary doesn't really favor either. So, just as we've seen before, we have to look at the nucleophile or base to see what's going to happen. So we just have to ask ourselves, well, what do we have? Do we have a strong nucleophile and a strong base, or do we have something different? Now this guy we know, because we've seen it up here, OCH3- is a strong nucleophile and a strong base. So this secondary alkyl halide doesn't tell us whether E2 or Sn2 is favored, so it could be both. And if you can see that this is a strong nucleophile and a strong base, it also doesn't tell us which is favored. So what do you guys think might happen? Well, if our nucleophile and base and our substrate doesn't tell us which one of the two occurs, then typically what happens is we just see both. Okay? So we'll see both E2 and Sn2 products. So when you see something like this, what you're looking for is to draw out two products. One which we'll call the E2 product, and then one which we'll call the Sn2 product, and we'll just deal with each one separately. Now the E2 product we know is going to be the, actually let's do the Sn2 first, that's the easy one, because we've seen this before. Remember, for the Sn2 reaction, all we do is kick out the leaving group and replace it with the nucleophile. But the thing we have to remember, all of you, is what happens to the stereochemistry in the Sn2 reaction. We know, well hopefully we know, is that the nucleophile attacks from the opposite side of the leaving group. In other words, oh you bastard, what is going on? You bottom face. Alright guys, my software has chosen to have a bit of a baby here. Did this last week when I was doing some tutoring, and basically I think the point is, you know what, let's fuck this up as much as we can for Dr. Payton, so he'll have such a lovely, lovely fucking day. Oh, sorry, I shouldn't be using the word fuck, but I did. La-di-da-di-da. Okay, well I just need to start writing a load of bollocks here until hopefully the pen sorts itself out. Oh, little shit. Sorry, I should stop talking. Alright, so I'm just doing this blah-de-blah bullshit to try and get things back. There we go, there we go. My, that was a lot of swearing, wasn't it? Sorry about that. Okay, let's start again. Okay, so remember we had the E2 and the Sn2 products. Let's hopefully do this again where it doesn't get all messed up. I'm going to cross my fingers and whatever other things I can cross too. Okay, now if the leaving group was on the wedge, of course the nucleophile is going to come in on the dash, and what do you know? Oh, it works. Okay, there's the nucleophile. Of course the hydrogen's going to be there. There's our Sn2 product. So now we've got to figure out, well, what does the E2 product look like? Well, of course we've got 5 carbons, same as we did before. And let's just be careful about this. We know there's our alpha carbon. So one question to you guys would be, well, how many beta carbons do we have? Well, in this case, we have 2. Beta 1 and beta 2. And remember I said before, for an elimination reaction, I'm going to be asking for you to show the most stable alkene product. Now, is that going to be the result of proton abstraction from B2 or from B1? Well, from beta 1, this is right on the end of the chain, so the double bond would go between alpha and beta 1. If it went between alpha and beta 2, though, that would be a di-substituted alkene versus mono-substituted here. So therefore, according to the Zaitsev rule, because we want to form the most stable alkene product we can, that's what we would see. So for a secondary substrate and a strong nucleophile and base, we form both elimination and substitution products. The question's a little bit less challenging when we have something like this. Now, I don't know if you guys remember this from the last video. There are some species that are classified as non-nucleophilic bases. In other words, strong bases, but weak nucleophiles. We talked about the T-butoxide. We talked about this 2-ring fused amine compound that's big and bulky. Anytime you have something that's big and bulky, you can throw your nucleophilicity out the window. Therefore, the Sn2 product, let me draw that a bit lower. Because it's such a poor nucleophile, you can take that Sn2 product and say, it's not going to happen. With something that's a weak nucleophile, the elimination is going to happen predominantly. We still follow the Zaitsev rule, though, and you'd form the most stable alkene product. So there we go. So just to summarize, we're talking about strong bases and nucleophiles here. So with a primary alkyl halide, strong base and nucleophile, because primary alkyl halides favor Sn2, you see Sn2. For tertiary alkyl halides, if you've got a strong base and nucleophile, you get E2 because the tertiary substrate favors elimination. Zaitsev rule applies to form the most stable alkene product. When you have a secondary alkyl halide and a strong base and a strong nucleophile, because both of them favor both mechanisms, then both occur. May not be in a 50-50 ratio, but that doesn't matter. You get 2 products. And then for a secondary alkyl halide, when you have a strong base and weak nucleophile, you're going to see predominantly elimination. All right. Bear in mind, if we had this strong base and weak nucleophile here, we again would see predominantly E2. All right. Okay, so that is how to predict between Sn2 and E2. Hopefully that is a little less non-cloudy.